Given an n by n 2D matrix representing an image, you are asked to rotate this image 90 degrees clockwise. How can you do that in place? That's about today's video. Let's get into it. Hi everyone, this is Steve here. Today we're going through LeetCode problem 48, rotate image. This is a very classic programming or interview or math question. Let's take a look. You are given an n by n 2D matrix representing an image. We are asked to rotate the image by 90 degrees clockwise. There is a note here. You have to rotate the image in place. That means you have to modify the input to the matrix directly without allocating another 2D matrix and do the rotation. Of course, you can do that. Of course, that's going to be a lot easier, but you're not allowed to do that. But that's the fun part. That's the meat of this question. Let's take a look. Give an input matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the given input. And we are asked to rotate the matrix in place such that it becomes this: 741, 852, 963. How it becomes like this, how it rotates like this, is because we rotate this matrix 90 degrees clockwise. 90 degrees clockwise. So you see 1 becomes here, 2 becomes here, 3 becomes here. So it keeps rotating 90 degrees clockwise. Now we have gone through the problem description. Let's think about how we can tackle this problem. So first, the very easy brute force solution is that we can just allocate a new matrix. Of course, that's not allowed, but I'm just going to talk about through the idea there, how we can actually implement that. We can just implement a new 4x4 matrix, right? At the very beginning, it's going to be all filled with 0. So a 4x4 matrix is going to be filled with 16 zeros here. Then what we will do is that we can just copy row by row, 5, 1, 9, 11, right? Where are we going to copy those? Just look at here, 5, 1, 9, 0. Then we'll just assign row by row into the new matrix column by column from right to left, right? 5, 1, 9, 11, then 5, 1, 9, 11 here. Then the second row is going to be copied to the last second column, which is 2, 4, 8, 10, 2, 4, 8, 10, right? And then the third row is going to be copied over to the third last column from the right, which is 3, 3, 6, 13, 3, 6, 7, 13, 3, 6, 7. The last row is 15, 14, 12, 16, then 15, 14, 12, 16. That's the very brute force. We are actually allocating a completely new n by n matrix to implement this. Of course, that's not going to meet the problem requirement. That's not going to be accepted. But we just talk about the brute force solution. A slight variation of the total brute force solution, which is to allocate the entire n by n matrix to do the rotation. We can use a temp array. So that way we can do it layer by layer. So here, for example, 5, 1, 9, 11, we'll move it to this place, 5, 1, 9, 11, and then move this array, 11, 10, 7, 6, 11, 10, 7, 6, move it from this last column to the bottom row. And then we'll move this one, 6, 16, 12, 14, 15, to its correct position, which becomes the first row, which becomes the first column, 16, 12, 14, 15. What we will move is a row by row, and we'll initialize a temp array to hold this, either this row or this column. That's one way. So this is the first layer, and then the second layer will continue to do that. Move 4, 8 to its correct position, which is 4, 8 here, and then continue to move 8, 6 to its correct position, which becomes the last second row, which is 8, 6 here. We can continue to do that. That's one way. Kind of in place, but still not completely in place, because we are taking advantage of a temp array, right? So how can we really do this in place using constant extra space? Well, we can tweak the second follow-up solution, the follow-up to the total brute force solution a little bit, which is instead of moving this entire layer or the entire row or column completely once, what we can do is we can just move one element at a time. That's going to give us constant extra space, which means we're rotating the matrix in place, right? So what we will do is that we just need to find every single element from its original position to its final correct position, right? Let's go through this. For example, 5 moved This is 5. 5 moved to here, right? So just think about how we can swap two elements. We use one temp variable, assign, basically 3 lines, right? Assign one number to temp and assign the second number to the first number and then assign temp to the first number. Then we finish the swap between two numbers. We just use one temp variable. So here, instead of 2 numbers, we have 4 numbers, right? So we always swap 4 numbers. That's going to imply that we're going to have 5 lines instead of 3 lines because we are swapping 4 numbers. But still, we only need one temp variable. We're good enough. So here, say, first we'll start from the very top left. Row 1 is row 0, column 0. So here we'll just follow the number swap logic. We'll save this one into a temp variable, and then we know who's going to take this position. So see here, 15 is taking this position. So we move 15 to this. We don't need to worry about we losing this value because we saved this one to the temp variable, right? And then who's going to take over this position? This position. So we saw 16. So we'll move 16 to here. Then which number is taking 16's position? Here we see 11. So we move 11 to this position. Now 11 is gone, right? 11 is gone. Now we see it happens that 5 should be taking the position of the 11. Then we finish the move. So basically 5 moved to here, 11 moved to here, 16 moved to here, and 15 moved to here. Then we finished this swap. Every number is in its correct final position. Then let's think about how that actually can work out, or we can how actually put that into the actual logic or code. Let's take a look. So here, you see, we'll just use another example. Still, it's 4 by 4, but I'm putting all of the elements in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so that we can follow the logic easier. This is the initial state, which is the given 4 by 4 matrix. And then, as I said, we'll swap just 4 numbers using only one temp variable. So that's in place. We're using only constant extra space. So what we'll do, we'll start from here, right? 1. So 1. We'll save this one into the temp variable. We'll call it top because this is in the top row, right? Next, what we will do is, so first round, I is 0, j is 0. We're starting from the outer loop. This is the outer loop. Next, what we will do is we will move the bottom one here, 13, to the top position. Override this. That's fine because we saved the value in the temp variable, right? 13 is in the final position, final correct position. That's the second line of the code doing the 4 number swap. Remember, we have 5 lines of swap to swap 4 numbers. Then next, third step is that, so I'm using the dark red color to indicate that this number is in its final correct position already, and using the yellow color to indicate that this is the number that we just moved. So in this round, in the third step, what we will do, step 1.3, in the third step, what we do is we move this number, 16, to this number, to this place, right? Because it used to be 13 in this place, but we moved 13 to its final correct position already. So we'll just override it. We put 16 to this position, right? This is step 3. Next step, we'll continue to do to move the last number, which is the 4th number. So it's the 4th step. We'll move the last number in this round into its correct position. Here it used to be 16, right? But 16 is moved to its correct position. So we move 4 to here. And then the last step, as you can imagine, last step is to move the first number, which we saved into the temp variable, in here. That's it. So at this moment, all of these 4 numbers, they are all in its final correct position. After, if we want to rotate this 4 by 4 matrix 90 degrees clockwise. All right, now we have finished the first. So this is going to be a nested for loop because we're going through row and column. So we have finished iterating through the first round, which is row equals to 0, j equals to 0, which is equal to row number as well, row index as well. All right, then we finished swapping the first round of 4 elements, 4 numbers. We finished swapping that. Now we'll start, so it's still going to be the first row, but we'll increment column by 1. So here, row index is 0. Column index is going to be incremented by 1. That means we're moving here. We're moving towards the right. So we finished this one, this one, this one. These 4 numbers are one group. They are swapped, right? They're rotated 90 degrees clockwise. Next is going to be this. Now we save this number, top. We still save it into a temp variable. We do the swap. So this number will continue. So you see, I is the row index 0, 0. J is the column index incremented by 1. We're still in the outer loop, which is this one. This is the outer loop, and then this is the inner loop. So this one. Next step, what we'll do is, since this one we have already saved into a temp variable, we can move the element that should be in this position as its final position, which is number 9. Then we'll just move this one to here, right? This is step 2. Step 3, we'll move, since this number previously it used to be 9 here, but 9 moved to its final correct position, which is in dark red color. We'll move the number that should be in this position as its final correct position, which is which number? 15. So we move 15 here. Then next step is we move this number. This number needs to be in the position where it used to be 15, right? So we move it here. This is the 4th step. The 5th step is the final number, which is the top number that we saved into the temp variable. We'll put it into its final correct position, which is here, right? After these 5 steps, we finished the second swap, the second round of swap, which is to swap another 4 numbers, rotate the second round of 4 numbers into its final correct position. So then we'll continue with the column. Column is going to be incremented by 1. So I is still 0, but column is going to be 2, from 1 to 2, which is this number. So we'll save this number into a temp variable, you see here. And then, so this position could be overwritten by, apparently we can see it's this number, 5. So we move 5 here, continue. 5 is in the correct position, it's safe to be overwritten. So 14 moved to here. Then 14 is good to be overwritten. We move 12 to 14's position. And finally, we'll move the 3 that's saved into the temp variable into 12's position. Now the outer loop is done. It's completely finished. Every single number in the outer loop is in its final correct position. What we'll do next? Of course, the inner loop, right? We'll continue to do the same. Start from here, but this time row index is going to be incremented. So last time row is at 0. Row index is starting from 0. Now we'll increment row. Row needs to be incremented, so row starts from I. J is always starting from where row index is started. So that means we're always starting from here. We're always starting from the diagonal. We'll talk about that a lot more in just a second. And now let's see. So we saved 6 into the temp variable. So this position could be overwritten. Who should move to this position? 10, right? So we move 10 here. Now 10 could be overwritten. 11 moved to this position. So now 11 could be overwritten. Which number should go to this position? 7. So now 7 is good to be overwritten. So which number? 6. 6 should be moved to this position. Now at this point, the inner loop, this is a 4x4 matrix, so there are only 2 layers, outer layer, outer loop, and inner loop. That's it. So we're done with rotating the 4x4 matrix. Now let's put coordinates into the picture so that we can actually understand how we're going to write the code. Let's see. This is the initial state, 0, 0, 0, 1. So the first is the x, which is the x coordinate. Second is the column coordinate. First step, x1, we're just, because there are multiple rounds, but it's always 5 steps, 1, 2, 3, 4, 5. So this is the step 1, we save the top. We save 0, 0 into the temp variable. Next, we move the left to the top. We move the left to the top. 3, 0, move to 0, 0, right? Next step is that we move bottom to left. We move bottom to left. 3, 3 to 3, 0. Step 4 is that we move this right to bottom. This right, 0, 3 to 3, 3. Step 5 is that we save the we move the temp variable into right, into 0, 3. These are the 5 steps that we'll have to do. We have finished rotating the first round of 4 elements. All of these 4 elements are in the correct position, just to help us better understand how we can put the actual coordinates, the numbers, into the indices. So let's go one more round. So here, this is the second round. We'll increment the column index, so j becomes 1. So we're starting from this number, right? We're starting from this number. So these numbers are going to be swapped with other 3 elements, which are these 3, right? These 3. This one go here, this one go here, this one goes here. These 4 numbers are going to be swapped. Then just one more round, then we're done with this column index, this inner for loop. So here, this is we increment j again to be 2. Now 2 is this number. This is the starting point of this rotation, of this iteration. This number apparently is going to be swapped with other 3 elements in the outer loop, so it's these 3. Now let's take a quick pause and think about where do we stop? At what point does j stop? So j is 2. Right now it's from 0. J starts from 0, which is where the row index is. So we start from here. And goes from 0 to 1 to 2. Now we stop here because here is the correct position, final position for a previous number, which one was used to be here, but now it's moved here. So apparently we don't need to rotate this one anymore because this one has been rotated already. So that's the upper bound. That's the boundary of the column index. So how do we denote that? That is j is bounded by 3, right? So j is always must be exactly smaller than 3. How do we know it's 3? Since this is a 4x4 matrix, so this n is the length of the array, or column or row size of the matrix is this n is 4. So 4 minus I minus 1, that gives us 3. So the j, the column index, whenever we rotate, the column index needs to be exactly smaller than 3, than this boundary. Why do we need minus I? Because I is the row index that will keep incrementing. So let's say next time we start from here, the I is 0. No, the I is not 0 anymore. I is 1. So we need to n 4 minus 1, so that is becomes 2. We'll talk more about that in just a second when we go into the inner loop. But here we say j is bounded by 3. J must be exactly smaller than 3 when we do the rotation. Next, what we'll see that we'll do the inner loop. Inner loop will increment I becomes 1 at this point. So it's going to swap with other 3 elements. So it's 4 elements going to be rotated clockwise 90 degrees. It's going to swap, it's going to rotate with the other 3 elements, these 3 other elements, right? This is the inner loop. And then we can see at this point, this entire 4x4 matrix rotation is done. So we don't need to increment I and j anymore. So I is bounded by what? I is bounded by 2. So I is only 0 and 1. You see, I is only 0 and 1. Then we're done. That basically means we only rotate the 1/4 of this entire matrix. Is that right? And we do it diagonally. This is where the starting point is. This is the starting point. We do it this way. From the top left, go along the diagonal. So it's always 0, 0, 1, 1. If the matrix is bigger than 4x4, then we'll do 2, 2. Row index is always starting from 0, and column index is always starting from where the row index started. That guarantees us, so it's always 0, 0, 1, 1, 2, 2, 3, 3. If the matrix is bigger than 4x4. That way, it guarantees us we start from we go along the diagonal, which is we only need to start from 1/4, the top left quarter, 1/4 of this entire matrix. We go this way. This one rotates to here, to here, to here, to here. This one to here, to here, to here, as you can see, right? So we go this diagonal. So this I is bounded by 2. 2 is the half of the array length of the matrix size. So that is 4 divided by 2 is 2. I only needs to go through half of the array. Why? Because, as I said, we only need to start from 1/4 of this entire matrix. That's it, because the other 3/4 of the matrix, they need to be rotated, right? This one rotate here, this one rotate here. So the starting point is only 1/4. So we can start from any quarter, but we'll just start from the top left corner. So it goes this way. Well, with that said, now let's think about how we can put all of the 4 indices into the actual code. How can we map that? Right now, these are concrete numbers, 0 to 4, right? 0 to 3, bounded by 4. Now we'll see. So the top one, we'll just start from 0, 0. Row index 0, column index 0. Top, this one, let's just look at the dark red. This is the dark red color. The top one, which is this, we'll save this into a temp variable, we'll call it top. This is the matrix, which is I and j. No problem with that, very straightforward. Now we'll get this one. What is this bottom number? How can we denote that in the index? That is the left one, sorry, the left one. The left index will use n minus 1 minus j. And the column index is just I. Column index is 0. You see, column index is 0 here. And the row index, which is n minus 1 minus j. In this case, j is 0, so 4 minus 1 minus 0 gives us 3, which is 3 here, right? This is the left. And then we'll look at this bottom element. How can we denote that? The bottom index is 3, 3. So what we have is size minus I minus 1, and then size minus row minus 1. That gives us 3, 3, 3. This is the bottom. Now the only one left is this, right. Right element. How do you note right element is 0, 3. So 0 is this j, it's 0. Then this 3 is n minus I minus 1. With this figured out, now we can take a look at the actual code. The code is going to be written literally like this. We just swap, we take turns, we start from this row, we start from 0, 0, and we go along the diagonal. We only need to start only 1/4 of this entire matrix. So here, the arrow stops here, 1/4 of this entire matrix. So the code will look exactly literally like this. So let's take a look at the code. So n is the matrix length. Then we start, the row is going to be bounded by this half of the array length. As we just described, I is going to be bounded half of the array length, right? We only need to go 1/4 of the matrix. So here, I is 0 and 1 for a 4x4 matrix. That's it, right? And then the column is going to start, we always go along the diagonal, By diagonal in the actual matrix, that means x and y, these two coordinates, they are equal. So 0, 0, 1, 1, right? So that's why we always start from the column index will always start from whatever the current I is, whatever the current row index is. And the column index is bounded by n minus I minus 1. That is why we have it here. It's bounded by this. And then we'll do literally what we just discussed, 5 lines of code, 5 steps, which is save the top. Next step, we move left to top. If we take a look here, this is left, we move it to top. This is second step. Then next is we move this one, bottom. Third step is move bottom to left, which is bottom to left, moving here, right? And then fourth step is from the right to bottom, move right to bottom. And last one is move top, which we saved into a temp variable here, and assign the top into the right one. Assign the top, a temp variable, into this one. Then next step, we'll rotate by column first. Once we are bounded, we reach the end of the column, then we'll increment row. And then after we reach the boundary of the row, then we're done. We finished iterating starting from one entire quarter along this diagonal. That means at that point, then we're done rotating this matrix clockwise 90 degrees. Right, that is one way that we can do to solve this problem, which is basically to follow exactly our thought process, to start from the top left quarter. We'll finish starting that entire quarter of this matrix and just keep rotating. All actually keep swapping all of these 4 elements in every single quarter of this matrix. Are there any other possible approaches or solutions to this problem? Yes. I was inspired by one of the posts in the discuss board for this problem. We can actually transpose the matrix first and then reverse either row or columns. So definitely there are other possible solutions. Now we'll just go through one of them. First, we're going to transpose from this matrix to this matrix. How we can transpose? If we take a deep look at this, between these two matrices, we can see the difference is 1, 2, 3, 4 is moved to here, 1, 2, 3, 4. 5, 6, 7, 8 is moved here, 5, 6, 7, 8. So first row becomes first column, second row becomes second column, third row becomes third column. How can we shift this? How can we transpose matrices like this? Okay, let's do it one by one. We'll start from the diagonal, the top left diagonal. Still, we'll go the diagonal. All of the points that lie on the diagonal is our starting point. That means I start from 0, J starts from I. Okay, so we'll just move one by one. Green just indicates the one that we're transposing to. Okay, 1 doesn't change. Why 1 doesn't change? Because I equals 0, J equals to 0. Then swapping is just swapping with itself. So all of the diagonal elements just basically swapping with itself, resulting in no change. Okay, and then here I is 0, J is 1, right? So it's going to swap with I is 1, J is 0. So I and J basically swap. These two are going to swap. So 5 and 2 become 2 and 5. And then I is still 0, J will continue to increment. I0, J2. This one is I2, J0. So basically swap I and J. That's going to be the two elements that's going to be swapped. 3, 9, 9, 3. Continue here. The difference, okay, now we'll just continue to do this. And so we finished the outermost loop, and then we'll continue with this diagonal. The next one is 6. I incremented by 1. So now I is 1, right? From 0 to 1, I is 1 now. Next, J increments by 1 as well. So here we start, I is 1, J is also 1. Now J is incremented by 1, so I1, J2 is here. I1, J2 is here, which is going to be swapped with I2, J1. We'll continue to do this. This is going to swap. Okay, now we're done with the second loop. The third loop is going to be I3, J3, which is this, 11. Then continue, J plus 1, 3 plus 1 is 4. 4, 3, 4. This is the index is going to swap with 4, 3, which is here. Now, the third loop is done. The last one is just swapping with itself because there is only one element on the diagonal. Then we're done. We're done with this transpose. Next step, you can see this is the intermediate matrix that we're going to reverse into the final output. This is the desired output. You can see every single row just needs to be reversed. 1, 5, 9, 3. The correct order is 13, 9, 5, 1. Sorry, this is 13. 1, 5, 9, 13, 13, 9, 5, 1. The same for the rest of every single row. So what we'll do is that we'll just reverse every single row. This one gets reversed, becomes this. Next one, this one reversed, gets this. Continue to reverse, continue to reverse. Then we're done. This is the correct answer. We'll just reverse first, we do a transposition of this matrix. Now we get an intermediate matrix. And then we'll just reverse every single row. Then that will be our final correct output. So what's the time and space complexity of this algorithm? By the way, the first solution, time complexity is O(n) squared, right? Because this is the length of the matrix is n, or the size of the row and column. They're both, because this is a square, so it's n. So n times n is n squared. Time complexity is O(n) squared because and we have to go through every single element. No doubt about that. Space complexity is O(1). So this problem, this solution is also O(n) squared time complexity because anyway, we need to go through this entire matrix once. And for this one, we go through this entire diagonal, not half of the diagonal, right? but the time complexity is still O(n) squared. The space complexity is also O(1) because we're not using any extra memory. We're not allocating a new n by n matrix. We're not doing that. We are just overriding, doing everything in place. This is doing transposing. This one swaps with this one, swaps with this one. This one swaps with. We're only using O(1) extra memory to swap, to complete this entire swap, this transpose and reverse. Now we can also quickly put that into code. Let's do that. Matrix length. First step, what we want to do is to transpose. So we'll start from 0. J always start from I. J smaller than n. J plus plus. Do a swap, which is only using one temp matrix I. J. Now we can change IJ to matrix JI. Remember, we're always swapping the two elements on the diagonal, 2, 5, 3, 9, 4, 13. That is indicated by these two indices, I and J, J and I. We'll just keep swapping them. And then here, matrix J, I, assign temp to it. So this nested for loop helps us do the transposition. Next step, we'll just reverse every single row. All right, now let's do that. We'll also have a for loop, start from 0. This is going to help us control every single row. Of course, you can also do another transposition and swap every single column. That's also possible, but the idea is the same. I'm just going to do it this way. You can practice doing it the other way. Then we'll have a start from the very left end and end from the very right end, which is n minus 1. Then we'll have a while loop to do the swap. Start smaller than n, we'll keep doing the swap. Temp matrix I, start matrix I, start, assign matrix I and to it, and then matrix I, matrix and temp to it. Now we want to start needs to keep incrementing and end needs to keep decrementing. That's the idea. So this I is the row number. This I is 0, 1, 2, 3. We need to keep going through every single row, and then we'll have a start and end to point at the left and the right. We'll keep swapping these two, right? 13, 1 swaps with 13, 5 swaps with 9. We'll keep doing this. That's why we have a while loop here. That's the idea. And now let's hit submit and see. All right, also accepted 100%, 100. Yeah, those are the two solutions. Time complexity wise, it's O(n) squared for both algorithms, and space complexity wise, it's also O(1) for both algorithms. Very interesting problem. I hope this video helps you understand this. And this video actually takes me 3 times longer time to make, edit, and put it online. So all that I'm asking you is just drop me a like, just smash the like button and subscribe to my channel. That's going to help a lot with the YouTube algorithm, and I really appreciate it. I'll see you guys in the next video.